Greetings from Science for the Public, and welcome to today's Contemporary Science Issues and Innovations via Zoom. Today, we hear about the latest work at the Large Hadron Collider in CERN, where collision of subatomic particles reveal the building blocks of the universe. Our guest is Markus Klute, professor of physics at MIT. Dr. Klute is an important figure in both the design and construction of particle detectors and in the analysis of the huge collection of data at the Large Hadron Collider. His group played a central role in the discovery of the Higgs boson there in 2012. And today, he'll give a presentation about recent work and future projects at the Large Hadron Collider. We are very honored to welcome back Dr. Markus Klute. Welcome.
So thank you, Yvonne, for having me back on your show. I prepared a set of slides which I'm going to share with you now. To give you a glimpse in what's going on at CERN and the Large Hadron Collider today. The idea of those slides are to first start with an introduction, specifically for those who are new to this topic. And then I'll talk about ongoing events, updates to the schedule, future plans, and also a bit of how the COVID-19 pandemic is impacting our research and our lives. You can see that this interview is not conducted in person, so this is one of the consequences, but there are obviously much more severe consequences for all of us. So this first picture here gives you shows you the CMS detector. That is one of the detectors in collaboration I'm involved in at the Large Hadron Collider, and it's in its open configuration. So this detector is located in France, very close to the Swiss border, about 100 meters or 300 feet under the surface. So for those who are really new to this discussion, the Large Hadron Collider is a proton-proton collider, also used for collisions for heavy ions, located in Switzerland and France. You can see here the city of Geneva in the background and also the French Alps. It's a large facility. The tunnel length is 16 miles. And there is about 4 large experiments which are shown here on this picture who record collisions of protons and protons at the Large Hadron Collider. Maybe a few words of history. So CERN was founded in the 1950s in order to restart research in Europe after the Second World War, in order to bring nations and people back together after this horrible time, and conduct research, pursue common goals and conduct research with a peaceful objective. And since then, this concept is being international, bringing people together is working very, very well. And it shows again in this very difficult times we are in right now. But how does it work? What are we doing? So we start basically with a can of hydrogen. We strip of electrons of protons, and then we let those protons ride on electromagnetic waves in order to accelerate them. And we don't do this one by one. We put those protons in bunches. Each of those bunches has 10 to the 11 protons, and there's about 2,000 of those bunches circulating in both directions in this ring, again of a length of more than 16 miles. Then we bring at dedicated points. One of those points is where my detector, or our detector, the CMS detector, is located. We bring those protons to collisions. We make the beams very, very tiny and bring protons to collisions. And then what we actually observe is the collisions of the constituents of the proton, which are quarks and gluons. And then this picture here shows you a visualization, and we'll talk a little bit more about those, of one snapshot in time, recording collisions of protons. And we can use those pictures, visualizations, we use computer programs to do that in order to extract physics from those collisions. So you might ask, why do we need so many protons, and why is this actually very hard? The interesting physics processes we want to study don't occur very often in proton-proton collisions. It takes about 10 to the 11 proton-proton collisions to produce on average one Higgs boson. And then in order to study the Higgs boson with precision, we need to produce many of them and record them. That gives you the scale of the problem. This diagram here shows you this probability. This is called a cross-section in the lingo we are using, but you can read it as a probability. There's a total cross-section, the total rate of collisions if you want, and then you have to go 11 orders of magnitude down in likelihood to produce those Higgs bosons. This next picture here shows you, and I think it's just a beautiful picture of the CMS detector. Again, this is during some of the maintenance work. The detector is open. We have the capability to take the detector apart. Each of those parts weigh up to 2,500 metric tons. So they're gigantic. The size of this experiment is comparable to a 5-story building. And you see in the very center here, a silver looking pipe. In those pipes is where the protons pass by. Most of them pass by our detector. Only few actually are brought to collision. So the protons go in, they're being brought to collisions, and in the collision, in the center of the detector, we produce then new particles in the collision, and they travel outside in the detector. So on the next slide here is the same detector. It's still the CMS detector. So once those collisions occur, the particles travel outwards. And the first thing we try to do is measure the momenta of charged particles. And we do this without disturbing the particles too much. And because we have the detector embedded in a large magnetic field, we are able to measure the momentum of charged particles. And then as a second step, at least some sort of particles, some species of particles, they are stopped in heavy material. And we call those calorimeters. So the particle slam into the material and they leave all the energy. And because they do this, we can measure how much energy they carried. So we use the detector to measure all those individual particles, up to 1,000 particles in each collision. We measure their energy, we identify their type, and we measure their momentum. So that is the underlying mechanism, the purpose of those detectors. And you can think about them simplified as cameras which look at collisions, and 40 million times per second they take a picture, and then we'll analyze those pictures. So here's one of them, a very selected one. It shows a candidate for a Higgs event. So all the physics is based on probabilities. When we look at a specific events, we cannot really tell which specific process actually occurred, but we can associate a probability of a specific event to correspond to a physics process. So here, this is again a side view of the CMS detector, and you see a number of interesting features. There's 2 red lines. Those are particles reconstructed as muons. They stem from a particle called a Z boson. There's 2 extra signatures in there, which are little green lines in the center. Those are stemming from electrons and positrons, also consistent with coming from a Z boson. And putting everything back together allows us to reconstruct this Higgs boson, or at least we are certain that this is a candidate for a Higgs boson. Again, the same detector on the next slide. This is a picture of a very different event, but also a candidate for a Higgs boson. Here, we identify 2 energy positions which are consistent with coming from a photon. So those 2 photons themselves then can be reconstructed, and we can infer back that a Higgs boson might have been at the center of this collision. So this is kind of gives you a little bit of an insight in how we use the detector then to infer the physics. We have individual particles, and from those we reconstruct what might have happened within the collision. But why is this interesting? One of the underlying questions, and there's many questions which can be answered with the physics we do. One of the, for me, the most important is, how do elementary particles acquire mass? And this table here gives you just a visualization of the known particles, the ones we identified and discovered in the last 40 and 50 years. And what's plotted here is the mass of those particles. And what you see is that the masses differ, again, by orders and orders of magnitude. The heaviest known particle is the top quark. This was discovered in the 1990s in the US at Fermilab, close to Chicago. And the lightest, probably the most known one, is the electron. And you see the orders of magnitude different in their masses. So what mechanism gives them mass? How do they become massive? Why are the masses the way they are? And while this might seem like an academic question, if you wonder, about sizes of atoms, the size of molecules, those are determined by the mass of an electron. If you wonder why a proton is stable and a neutron is not, that is determined by the mass difference between the up quark and the down quark. And the masses itself, they govern the evolution of our universe as a whole. So those questions are really, really deep and for me, extremely interesting. But then, we have a theory which, allows us to calculate and predict interaction of particles. And part of this theory is the content of the particles. So you see here, again, the same particles as shown on the previous slide. There's quarks and leptons. Those are, we call them matter particles. And then there's force carriers, the Z boson, the W boson. They're responsible for the weak interaction, responsible for the burning in the sun, giving us the energy we need every day. Photons, you know them, if you switch on a light bulb, there's light coming, those are photons. And then there's a gluon, which is responsible for holding quarks together inside objects or particles like a proton or a neutron. So far, so good. The Higgs boson, in this picture is nicely illustrated. It sits somehow in between and connects all of those things. And as I was just explaining, the Higgs boson, or the mechanism which creates the Higgs boson itself, is responsible for the mass, or gives mass to those elementary particles. Okay, so we discovered the Higgs boson, and now we are trying to measure the Higgs boson to the highest precision, or the properties of the Higgs boson to the highest precision, in order to figure out whether or not this theory describes nature, and whether or not we can learn new things about it. And we did this. So this plot here shows you the relation between the masses of the particles and how strongly they couple to the Higgs boson itself. And you can see nicely there is a line going through the individual particles again, the top quarks, the WZ boson, the bottom, the tau, and the muon. Those are the particles for which we are able to probe the coupling of the Higgs boson to the particle itself. And the fact that there is a linear behavior, this line, between the coupling and the mass itself tells us, or allows us to infer, that the masses are given through the coupling to the Higgs boson. So we have shown here that the Higgs mechanism is realized in nature, and that particles require mass through the coupling to the Higgs boson or Higgs field. So this is fantastic, but how do we go from here? So the key here is to measure those couplings, or one of the keys, to measure the couplings of the Higgs bosons with ever more precision in order to find deviations from the expectations, which then tell us new things about nature. So that is part of our program now and moving forward. And it's not just making those error bars smaller and smaller. We also want to go down the line and see whether or not this muon, or so-called particles of the second generation, the lighter particles, have the same behavior as the heavier particles, which we are already able to probe. The most particles you see around us, all particles you see around us, are of the lighter nature. The heavier particles which we are able to probe are particles we produce in our laboratories. So the question is, are those lighter particles also behaving like the heavier particles which we are able to test so far? And we have made excellent progress on, going by having more data, being more sensitive to study those particles. Okay, going back to this picture. Now we have a complete theory, and it's great. And all our measurements are in excellent agreement with our theory. We haven't found any particle which is not in this block, almost. So this is not the complete story. This is not the end of the story. And there are certainly more things to be discovered in nature. So this standard model fails to explain observations we've already made in nature, which means there is something else to be discovered. That's clear. What there is to be discovered, that is less clear. So the only option I see, at least, is that we try to, get into a discovery mode where we, observe nature. We try to make experiments with the highest precision and try to infer what is next. how can we explain the other unobserved but unexplained phenomena in nature? And some of those examples are, very well and widely discussed in public literature. Dark matter. We have cosmological evidence for dark matter, but we don't know what dark matter actually is. This is one of those questions where, the structure of our universe depends on this form of matter, but we don't know what it is. There's also an asymmetry between matter and antimatter. Where does this come from? We don't know precise answers. We don't have precise answers to this. And there's more. I didn't talk about gravity in all of this, but in our standard model, in our standard theory, we are not able to describe gravity. It's so weak, it's not relevant to our experiments, but our theory also doesn't describe gravity in this context. And for me, and that is a choice or a theoretical bias I might have, but the Higgs boson might give us answers to this. So that's why I'm personally interested in studying the Higgs boson with more precision, and a large part of my community agrees with me, so I'm not alone in this opinion. All right, so the Higgs boson is a cornerstone of our physics program, and I just explained how we can use the interaction of the Higgs boson with standard model particles, with the known particles, in order to learn more about the Higgs boson. But the Higgs boson might also give us a hint in what dark matter is, by being a particle which is kind of giving us a window, a portal into this world of dark matter. It might play different roles. There might be additional Higgs bosons. Many theories which extend the standard model include additional Higgs bosons. So the search for those is extremely important. And then the last question, which is super interesting, is how does the Higgs boson itself get massive? It's heavy. We know its mass. We have measured the mass. It's about 125 times as heavy as a proton. We measure this with very high precision. But the mechanism in which the Higgs boson acquires its own mass is predicted, but not measured. So can we close the loop on the Higgs boson itself with measurements in the future? Those are some of the ways in which we can use the Higgs boson in order to learn more about nature. So how do we do this? We collect more data, and we don't do this linearly, just waiting and waiting and waiting. We increase the intensity of our machine. So this might be a complicated plot to look at, but it's a timetable started in 2010 with the start of the LHC and ends in 2038 with the end of the currently understood program of the LHC. And what we are trying to do is not, year after year collect the same amount of data. We try to increase the intensity. And that allows us to then more accurately measure things like the Higgs boson, but also look for new physics. There is a prize which comes with this. There's actually a number of prizes which comes with this. One is we're not colliding one proton with a proton again. We do many proton collisions at the same time. And you see this in the picture. Those visualization I was explaining before, they become more and more complicated. So, this one picture on the left shows 20 proton collision at the same time. The one on the left, 200. And we're aiming to be in the area of 200 collisions at the same time. So an order of magnitude more than what we typically do today. And that requires that we update our detectors, that we read them out faster. The volume of data increases. So there is a technical challenge involved in doing this. So over the last, let's say, 6 or 7 years, we developed an entire program. And I'm showing this here for the CMS detector. The other detectors or collaborations developed similar programs. And you don't have to go into detail. The purpose of this slide is that it's complicated. We have to make a lot of changes to our detectors in order to be able to extract the physics we want to extract in the future. And challenges are always opportunities, meaning that we can use new technologies, updated technologies, starting from running machine learning algorithms on FPGAs, which are programmable computers, if you want, towards new technologies we are using in some areas where measurements become extremely challenging. So this is exciting from the technological point of view. Those advances are important for the field, but they can also translate into other fields of science and into the community or society in general. So this is an easier plot to read, but let me explain it. So this is a calendar starting from last year, 2019. currently the LHC is in a shutdown period. And so we are now in the middle of 2020, and ideally we would have started to prepare for the next run. However, COVID-19 happened. And I'll talk more about the implications, but what this means for us is that we had a period where the laboratory was just closed. Only a few personnel was allowed to enter the lab to make sure that nothing really breaks, but the lab was closed. So we lost about 3 months of this time. CERN is currently starting to open up again in a phased approach, trying to keep everybody safe. But it's not just CERN, it's all the laboratories and universities around the world which are impacted. So there is a longer latency in making sure that we can restart the machine. So we revisited the program. The CERN, as a group, we looked at this. They revisited the program and decided to not have physics data taking in 2021. Those are those green bars. They are our proton physics data taking period. So we restart in 2022 when the machine is fully commissioned, and then take 3 years. Integrated over those period, which we call 1-3, we will not lose much physics. So we rearranged the schedule to do some work which was scheduled later, to do this earlier, and trying to fully exploit the time we have in order to make those collisions. Then there's another long shutdown coming up, for which we make those larger changes to the machine and the detectors, which are, for example, explained on the previous slide. So this is an enormous program ahead, and that then starts this period of high luminosity, really high intensity LHC operations. And then this goes in this calendar till 2036, but there's a number of extra years coming up. So the schedule for the LHC or high luminosity LHC goes till 2038. All right, before I discuss what we might do afterwards, let me just talk on a few slides or one slide about COVID. So clearly this is a terrible event and it's not over yet. We are by far not reaching the end of this episode in our lives. And when you live and work in an international and worldwide distributed collaboration, you see, not just from the news, but day to day, the impact this has on the people you work with. I have many collaborators who got sick. We had collaborators who passed away in recent months. So it's really, really terrible. The impact then is also on, as I was saying, laboratories and universities being closed, everybody working from home, which has challenges different to everybody. Some people have little children they have to take care of. Other people just are alone, and that's problematic as well. And then there's economic impact and situations people need to deal with as well, of course. But there's an aspect which works very well for us, is that as an international collaboration, we were already able to work from home, to connect from wherever we are, to have ways to communicate very well. And this has shown for us not to be a problem. We have a Zoom meeting here. We have been doing video meetings since I remember. So this kind of communicating is not really new for us. And it's working actually quite well. Another point which I find very fascinating, and I'm very proud of my collaboration and the collaborations at CERN as well, is that we did not just passively look at this. We tried to ask the question, what can we do to help? And so over the last 4 months, there was this deep sense of solidarity, trying to come up with ideas to help. And those ideas, just to give you a few examples, range from developing engineering departments, developing low-cost ventilator designs, ventilators which cost less than $1,000, which you can just produce very quickly and ship around, mass productions, face shield productions, and things even like a door opener, such that you don't have to push the door button or the elevator button. You can print those with 3D printers and just distribute them. And some of those are useful for our own in order to enable our research, but we have in some areas being able to produce them at mass and distribute them and hand them out. So at CERN, there was a group established, which is called CERN Fight Against COVID. And my collaboration, the CMS collaboration, made fantastic contribution to this. One aspect I was involved in is making computing available to people who try to understand how to cure and how to understand COVID itself. And so there is a program which is called COVID, Folding at Home. And we have made very significant computing contributions and also have discussions with the people behind the software and how to improve their infrastructure in the future. So it's not just the immediate help, but talking to people long-term and figuring out and how we can improve the situation for their science. All right, I have to be aware of the time. As I was saying, what we do well is communicate, and what we can do well worldwide distributed from home, from wherever we are, is analyze our data. So we continue to do this very effectively over the last 4 months. And we came to a very important milestone to us, which is the publication of our 1000th paper. So over the last 12 years, with a rate of about 100 papers a year, we published physics results of really high quality and with a wide spectrum. So I talked about Higgs physics, about 100 papers, a little bit more than 100 papers out of those 1000 deal with Higgs physics. But there is 900 other papers who deal with other very exciting physics too. So this is just a very fascinating milestone. And when I go back and I looked at some of the papers we wrote on this way, you know, paper number 100 was a Higgs paper. I was, you know, had the pleasure of editing, which looked at Higgs decays to tau, for example, to tau leptons. And so, you know, this is, you know, has a personal touch to me, but it's also a showcase how productive this community is, and even in this difficult time. Another thing which happened over this period and was delayed to some degree by COVID was that in Europe, we had a program over the last almost 2 years in order to define the strategy for the particle physics community. We do this in Europe and also in the US every 5 to 7 years. We ask the question is, where do we want to go as a field? What are our priorities? And that then informs everybody else and sets priorities for timescales of 5 to 7 years. Particle physics experiments can be large, and they have large timescales associated to them. You saw the calendar for the LHC and high luminosity LHC. So this European strategy was released last week. It has the idea to provide this near and long-term vision, and very clearly stated, the idea is not to make steady progress, but to significantly extend our knowledge. And again, as I was saying, there's a similar process in the US right now. It's starting here. This is called SNOWMAS, and will conclude next year. All of those endeavors are international. They're not located or limited to Europe, but the European strategy is specifically a strategy which then is going to be adopted by CERN and implemented by CERN specifically. So the key findings, and there's many findings, it's a lengthy document, and I just distill here 2 main points. One is that the LHC and the high luminosity, they remain the world's primary tool to explore the Higgs bosons and this energy frontier, trying to gain knowledge in this microscopic world. And then the second point is that there is compelling scientific arguments for a new collider, for a new electron-positron collider, which operates as a factory to produce Higgs bosons in order to get yet to another order of magnitude more precision and fundamentally learn new things about the Higgs bosons with this tool. So let me just say, because there's a number of articles and the viewers might have read those, this strategy doesn't mean that we are going to take a spade and start digging a tunnel. This means that we will spend the next 5 to 7 years exploring and pinning down how we want to build a machine like this. And one of the leading contender, I would say, is a large facility at CERN, around CERN. You saw this very large Hadron Collider, LHC, and you see this dotted ring here. It's very easy to make a plot like this. You just take a map and draw a circle. But behind this study, for the last 6 years, we studied the feasibility of such a machine with geological studies, with explaining what the requirements are, what the physics potential is of a machine like this, and also how we could actually build it. But those studies now have to be intensified. They have to be more concrete, and that is the plan. And that is kind of the the mission given by the European strategy to the community is to move forward in this direction. Again, the earliest one could start building a machine like this is in about 10 years from now. And then it takes time to actually build it. All right, let me conclude. I think there's significant progress. We saw this 1,000 papers. Behind each and every paper, there is scientific progress. And I think especially in our understanding of the role of the Higgs boson and the nature of the Higgs boson has improved tremendously over the last couple of years. The impact of COVID-19 is felt in many ways. There's many personal stories, but there's also the impact on the society and the way we conduct science, how we travel or not travel, how we conduct conferences, for example, which is more than a disturbance to the way we work. Yeah, but besides that, we are preparing for the next one. It's now scheduled to start in 2022, and the idea is to triple the amount of data we have. And then the next step to this is to get 20 to 30 times the amount of data, and it's really to illuminate, sorry, that's a bad typo, illuminate the Higgs boson and has potential for discovery. And then in the last point I wanted to make is that we have we had discussions on the long-term future of our field, and that has concluded in Europe. It's still going on in the US, and that sets the stage for the next 5 to 7 years. So with that, I concluded, and I probably should stop sharing my slides. Thank you.
Thank you, Dr. Klute. That was very interesting. The other thing that I'd like to point out is the slides are very informative. So thank you very much for that. I'm sure the viewers will get a lot out of that. We really appreciate your giving this presentation and getting us up to date, and enjoyed seeing you again too. Thank you very much.
You're very welcome.